Okay, Arianna, we're live, so I think we can start the event now.
Okay. Good afternoon, everyone, and thank you for coming today, for taking some time to join this event on future housing retrofit. I will present two case studies developed during the EU-funded IFORE project that started in 2010 and ended in 2014. I think that despite the fact that the project ended more than 5 years ago, there are some lessons that are still very relevant today, and that these can be useful to practitioners that want to take on the challenge to retrofit. The proposed takeaways are the most effective retrofit measures, facts and myths, lessons from post-occupancy interviews, what residents say about the retrofitted homes, budget, what is the cost of retrofit, climate change, how to avoid overheating in retrofit, and next steps, how can practitioners unlock the business potential of retrofit. This last point will be part of the discussion, and I would be grateful if during my presentation you could write some suggestions and ideas in the question box that we can discuss together in the second half of this event. You can ask any question in the question box during the presentation and we'll answer them at the end. I think that retrofit presents some design potential and that as architects we have an important role to play. This is some background of the project that started shortly after the Climate Change Act became law in 2008. It was a cross-border collaboration between England and France, and in line with the Act, its aim was to reduce by 80% the carbon emissions of 200 houses. A 60% reduction was to be achieved using traditional measures, such as insulation, air tightening, windows, doors, and boiler upgrade. And the further 20% was to be achieved with the use of renewable systems and a change in the occupant's behavior. A comparison of the UK and French housing stock shows that the UK stock has about 10 million less houses than the French and a similar population. This is data from 2012. And this is the project location. The project is located on the two sides of the channel. In England, the houses are in Kent, on the Isle of Sheppey, and in France, they are in the region of Pas-de-Calais. The towns have similar climatic conditions, but different house types. The challenge was to find similarities between the house types in order to implement comparable solutions. Two universities and two housing associations were involved in the two countries, the University of Brighton and Amicus Horizon in the UK, and the University of Artois and Pas-de-Calais Habitat in France. In both countries, some of the two-story houses were bought as part of the right to buy, and owner-occupiers are interspersed between social rented houses. At the beginning of the project, the teams carried out a number of surveys and tests. Blow-a-door tests, thermographic photographs, to identify the leakage points, and calculated the existing and future U values of the houses. In England, the air permeability was measured between 3.8 and 14.2 cubic meter per square meter per hour at 50 pascals. And after the retrofit, in some cases, a substantial reduction was made. The houses in the UK are a mix of bungalows and two-story terraces. They are built between 1945 and 1964. with brick and block construction. Some of these houses have benefited from government grants for the installation of loft and cavity wall insulation. The subcalculation shows that the houses are very inefficient with an EPD band E. The houses in France are also a mix of bungalows and two-story houses. But the mix is more diverse in terms of form and type of construction. The houses are slightly more efficient. They are built more recently with an EPD band CD. So we conducted some dynamic thermal modeling of the house types to evaluate different specifications of the building works. We modeled a base case, the building as it stands before interventions. And then we added to the models clusters of retrofit measures one by one. And we assessed the energy and carbon reductions associated to each measure. We modeled basic retrofit measures such as cavity wall, loft and external wall insulation, windows replacement, air tightness improvement and controlled ventilation, and VHR and boiler upgrade, and also more innovative measures such as supply air windows. The single most effective retrofit measure is the insulation, followed by the installation of the MVHR in an airtight envelope, and third is the air tightness improvement with controlled ventilation. The other measures also contribute to the overall reduction of 67% achieved in the models using traditional systems. Based on the initial surveys and on the modeling results, a matrix was created to assess the retrofit measures in function of the house types. We wrote 4 specifications that included similar elements and targeted the differences between the UK house types. The measures implemented in the UK are loft insulation, external wall insulation. The UPVC windows were refurbished rather than replaced and made more airtight. The doors were replaced, the leakage points were sealed. Depending on the initial air permeability of the houses, a choice was made to install mechanical ventilation heat recovery to those that could achieve better air tightness, and mechanical extrude ventilation was installed in the others. The boilers were replaced, and depending on the hot water demand, either solar thermal panels or photovoltaic panels were installed on the roofs. A small number of houses benefited from the installation of ground source heat pumps, air source heat pumps, and some innovative measures such as supply air windows and ventilated trunk walls. So these are for the UK houses, and the interventions in France. They opted for a bespoke prefabricated system that included the external wall insulation, the cladding, new draft proofing, and the supply air windows. Loft insulation was also installed in the houses. So the supply air windows, the first innovation. These are triple glazed windows with a path for air circulation between the panes of glass. So the air that enters the room is preheated by the solar radiation hitting the glass. Moreover, the heat that would otherwise escape from the room is entrained in the air path and used to preheat the incoming ventilation air. Therefore, the supply air window acts as a heat exchanger. There are different types of supplier windows. You can see a couple of them on the slide. This is a whole house system that pulls air in at the perimeter and extracts it from the kitchen and bathroom. Humid air from these wet rooms is extracted mechanically so that airflow through the rooms is created with enough pressure drop to pull air through the supplier windows. The other innovation that was installed in the houses is the ventilated trom wall. Trom walls are not new. They have been tested since the 1970s and are low-cost passive solar components that can be used in housing. This ventilated type of trom wall is one of the innovative solutions being incorporated into south-facing walls of retrofitted homes in both England and France. Within a composite trom wall, such as this, the solar radiation hits the airspace behind the glazing, and the heat is stored in a brick wall. In winter, vents in the lower and upper parts of the insulated internal wall allow the circulation of warm air that enters the room from the vent at the top. A simple system has been installed to avoid inverse air circulation when the wall is cold. A shutter in front of the glass is closed in summer to avoid overheating. In this way, approximately 30 to 40% of incident solar radiation can be used in winter, spring, and autumn as a contribution to the space heating demand. As part of the project, various engagement activities took place in both developments, with the involvement of school children and events for the communities that ran throughout the project. The community engagement team was on site and engaged with the residents by raising their interest in their home's energy performance. It was composed of a community investment manager, a green doctor, an energy advisor, an education officer, a team assistant, and a sociologist. In the UK, the Green Doctor was based on site and carried out two major questionnaires, one before and one after the retrofit. The Green Doctor also offered advice on how to reduce the energy consumption in the household and offered free gadgets to help the households manage their energy use. This was done at the same time as delivering the questionnaire. In France, the energy ambassadors visited the residents regularly and helped them to understand how to reduce their energy consumption. The topics of the questionnaire included questions on energy and water use and behavioral change. It was developed by a charity called Groundworks and adjusted by a sociologist from the University of Brighton. These houses were heavily monitored with various systems during and after the works. They were monitored with some temperature sensors before, during, and after. In the UK, a small number of houses, about 10%, received a monitoring and heating control device called Box. The rest was equipped with a smart meter. In France, the choice was made to give to the residents a tablet that indicates the consumption. The use of these devices was explained to the residents during home visits by the Green Doctor and energy ambassadors. The monitoring results show that the average internal temperature in the UK houses was actually below the set point temperature used for the simulations of 21 degrees centigrade. And in fact, some analysis of the heating bills show that the heating consumption was way below that calculated in the models. That seems to suggest that the houses were underheated. A development had many residents in fuel poverty. There were some important variations between households. Some had their internal temperature above 21 and some others had it much lower. The older residents had a warmer house generally. The graph shows the temperature monitored before and after the works. The graph below on the right. In a household that had the heating on in the month of February, the red line shows that the temperature after the retrofit is much more stable than it was before. And that indicates a more comfortable and healthy environment. The internal temperature monitored using sensors and heating controls was used to validate the models. So we inserted into the models the actual internal temperatures of some typical households that we monitored on site before and after the retrofit. And we also used the current weather files for those specific years. Using the degree day method, the validation shows a good reduction in energy of 33–44%. And these are some of the images of the UK development post-retrofit that show the interspersed owner-occupiers between the two-story retrofitted terraces. The bungalows were owned entirely by the housing association and had no interruption in the external insulation. The color choice of external render was made by the residents. In France, the choice of prototyping a bespoke prefabricated system was driven by the desire to innovate. And the local architect, Jean-Luc Collet, was involved in the development of the system. These pictures are taken in the architect's office and show some supplier windows that can be opened for cleaning purposes. And the vents at the top, that is for the air to enter inside the panes of glass. The first prototype was applied to a bungalow. The supplier air windows were manufactured in France in new PVC and inserted into the prefabricated system. A small number of windows were also manufactured in France for some of the UK houses and shipped across the channel. A local manufacturer from the region of Pas-de-Calais was involved in the process of making the prefabricated panels. And these images show the installation of the system on the bungalows, with some panels on the ground waiting to be installed. In collaboration with the sociologists from the University of Brighton, we developed a number of questions targeted at the summertime comfort and overheating risk after the retrofit, and did some post-occupancy qualitative interviews and focus groups with the residents. The residents discussed a topic during each focus group and also reported some of the issues that they were concerned about during the works. As well as the main questionnaires delivered by the Green Doctor, we also have some additional data that describes the experience of the residents during and after the project. These are some results from the interviews and focus groups and the questionnaires. During the focus groups, the residents discussed some of the issues that they had with the measures installed, such as the MVHR, solar thermal, the new boiler. Generally, the results of the second questionnaire show that the work of the Green Doctor was able to help the residents reducing energy in everyday practices. A simple spreadsheet program was made to predict the overall savings due not only to the retrofit works, but also to the additional renewable energy systems used. And as a result of residents' behavior change due to the impact of the Green Doctor. This has been based on national figures such as the manufacturer's predicted performance of solar thermal panels. The dynamic thermal models have shown a heating load reduction being achieved due to the retrofit works of approximately 40%. The pie chart at the top shows that about half of the reduction in energy is due to the physical works. A quarter is due to the renewable systems, and the remaining quarter to a change in the occupant's behavior. What is the cost? We have had 4 main specifications for the retrofit in the UK that differ slightly from one another, depending on the characteristics of the house types. And all these 4 specifications had a similar budget of about £15,000 per home. Some of the houses, the most airtight, included an MVHR, some others included a mechanical extra ventilation. Few houses had the supplier windows and trombones. The retrofit in France was more expensive. It was around 25–30K per house, but they achieved a bigger reduction in energy. And finally, how to avoid overheating in these houses. So the question is, does the retrofit reduce or increase the overheating risk? Are we making these houses worse or better than they were before? The modeling showed that the houses overheat less after the retrofit. That is because of the effect of the external insulation and reduces both the heating and the cooling load. However, when the thickness of the insulation is increased further, say to passive house level, the heating load reduces, but the cooling load does not change. Which might mean that in an envelope that is already well insulated, an extra layer of insulation does not help reducing further the overheating risk. When increasing the airtightness, that is, when making the houses more airtight, to passive house levels, for instance, the heating load reduces, but the cooling load increases slightly, up to 2050s, as a very fine balance. So as it gets warmer weather, by the 2080s, the airtightness improvement slightly reduces the cooling load again. This could be because as it gets warmer, there are some benefits in keeping the warm outside air out. And this is for you, for all of us, to think about how we can unlock the business potential of retrofit. So I'm curious to know whether you have any suggestions or questions about this project that I'd be very happy to answer. There is a question here. Is the trombe wall required to be installed to the whole south-facing elevation or just locally, the size of a door, for example? The images showed, yeah, the trombe wall was the size of a door. It's sufficient to actually produce a bigger improvement in the indoor conditions in terms of the heating, reducing the heating load. Yeah, but it can be installed, I guess, in the south-facing elevation, but yeah, it's a matter of deciding whether that's needed or not. In some climates, it might be more suitable. In some other climates, it's a bit less relevant. But yeah, in this case, it was the size of a door. Okay. So there are no further questions. So I think that this presentation will be published on the YouTube RIBA YouTube channel, so you can download it from there. You can view it again from there if you like. That's a very good question. If there are any grants for homeowners to encourage retrofit measures, there are some grants. I mean, the Chancellor has announced, I think in July, these grants, and the deadline was the end of September to apply for the grants. There were £2 million given to homeowners for retrofitting their homes. I don't know if you're still on time. There is a government page, web page, that anybody who's interested in this can look at and see whether it's possible to apply. I mean, £2 million is not a huge amount, but it's a business incentive that can help moving forward the economy. Any other question?
I think there's a
yeah, I can see them. Yeah. 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 This is a good question. Have you been able to apply any of the knowledge gained on projects since the trial? If so, have there been any further improvements? That's a very good question, because since the project ended, I've been trying to use this knowledge and the experience in my profession, in my day-to-day practice as an architect and as a sustainability consultant. And the reason why I wanted to show this project again is because I think that the idea of retrofitting the UK homes, as well as a lot of homes everywhere else in the world, really, that need that type of improvement, it's still an idea, and it's not really been launched or rolled out quite yet. That's why I thought that even though the project has finished over 5 years ago, it's still very relevant today. The improvements compared to 2015 mainly have been made regarding the combustible materials. There is a much stricter attention now to the use of non-combustible materials than there was 5 years ago, and that's because of the Grenfell disasters that has of course changed everything, especially in high-rise residential buildings. But I'm sure that even in low-rise buildings there would be there could be more attention with regards to the combustibility of materials. And I did work on those aspects as well, because as we know, the recladding of the Grenfell Tower was made with the purpose of reducing the energy consumption of the building. So, you know, that must not happen again, obviously. There's a question about the supplier windows. How much did the open glazing compromise the insulative value of the windows? How would the triple glaze supplier windows compare with double glaze with trickle vents? This is quite technical, but I mean, ventilation is part of the design of any building, so the building needs to be ventilated. The purpose of these windows is that the air that comes into the rooms is preheated by the sun, by the solar radiation, which is there all the time. It's just that we don't use it. So they act as a heat exchanger. It's kind of the same principle of mechanical ventilation heat recovery. The air that comes in is preheated, but in the case of the supplier windows, there is very little energy that is involved in that. So the vents can be assimilated to trickle vents after all. So the U value won't change as such. But actually, if we consider the hot air inside the panes of glass that is circulated, the U value goes down, obviously, because the window becomes more like it's insulating more. So the next question is, since the project was completed, have there been any measures or techniques which you think should be considered for retrofit? Well, yes, there has been quite a lot happening since the project was completed, past 2035, for instance, which structures around several figures that the retrofit coordinator, the retrofit designer that overlook the retrofit works. So there has been things happening since that, and also there is this whole concept of whole house retrofit, which we did apply in the projects because we had monitoring systems, and each house type had systems that were targeted at that particular house type, and with the use of the matrix, we were able to identify which solution was appropriate for that particular household with that particular consumption. So I think that prefabricated systems such as the one that was used in France and that is also quite is also popular in the UK. Is one of them, but also, I mean, nowadays we use drone surveys to do large-scale surveys, and that can be also useful to retrofit massively large developments. So there is another question about the triple glazed heat transfer window. Yeah, so this is another very good question. Whether the windows become dirty because of dust deposit between the panes. That was a very important issue, and in fact, the architect that designed these windows in his own office designed them to be open and cleaned inside. These particular windows that we've installed in new PVC, they had to be made. They were low-cost windows, so the panes of glass do not open. But there was a system that was designed that was able to actually clean the panes of glass inside with pressurized water, pressurized air, because of course that could be a concern. I find in retrofit there is a bridge between the practical knowledge and the theory. Yeah, it's true. That's what I also found, that as designers we can apply our practical knowledge of building materials, also building physics, and then see the results and measure the results. So I completely agree. With a limited budget, do you go for airtightness first or insulation? Well, they don't cost the same. I think they, it depends on the level of airtightness. Obviously, if it's just sealing with mastic, it has a cost. If it's about lining the internal walls, that has another cost. I think that, yeah, the external insulation is more expensive, but yeah, it depends on the budget. I think making an envelope airtight might be very cheap. It might be something that can be done. It can be done really cheaply, but it always depends on the level of improvement that one wants to make. Yeah, so I think every case needs to be assessed independently, case by case. Do you do any thermographic surveys? So thermographic surveys, they need to be done. They're very useful when we need to assess the quality of the existing buildings, because we can see immediately whether there are some air leakages and where those are, and whether the cavity wall insulation was patchy, for instance, it's been installed, but it's not maintained the original state. So that's a very useful tool. And also it's very useful after the retrofit to assess what the improvement was. So I think that in the case of retrofit is an essential part of the work to actually carry thermographic surveys. Yeah, so how can architectural practices take advantage of the retrofit trend? This is what I wanted to discuss with you, because I think as architects, we are fully equipped to take on this type of work. We can do it like exactly like any other building work that we do. So I think we should find a way, or at least discuss together. Maybe we need to lobby more, and because it's within our profession to actually refurbish buildings and design and build new buildings, and actually care for the aesthetics of our towns and cities. I think we've got all the abilities, potentials to take on this challenge, and we have theoretical skills as well as practical skills. Just a matter of getting a number of other professions that want to get in there as well, and I think that we are included, and that because we are built environment professionals, and that's, I mean, what we do all the time. It's not retrofitting. It's not different from what we do normally. So what color is the best for the trombo? Black, obviously. The bricks are painted black so that the heat is absorbed inside and stocked inside the brick wall, which is quite thin. It's just a layer of bricks. And that's why it's also important to shade the glass in summer, because that absorbs so much heat that it can become a source of overheating indoors. Yeah, so today's event will be recorded and uploaded on the RBA YouTube channel, so you can watch it again. And I mean, if there is no other question, I think you can close it. I hope you've enjoyed and that you've gained something from it. But yeah, by all means, to get in touch as well if you like to discuss these issues further.